So as I was saying that you see the overall method of how to determine what will be the nature of the fluid, especially for our offsetting, we have various methods. I will show you some other methods as well, but today this method that I am going to show to you, this will actually have a much more significant impact on how we determine uh, the interaction of the ink with that of the printing machine, because sometimes it may so happen just by measuring the viscosity, just by measuring the tack and the flow of the ink, it may not be sufficient parameters. These measurements of these quality assessment tools, they may not be sufficient metric enough in order to find out how these methods, how these inks will actually behave when they go into the press during printing. For this we have a one technique which is known as the which is basically known as the various techniques actually. So here I will show you two plate rheometer, okay. Before I go into the methodology of this test, let me also talk a little bit about the behavior of the ink in itself. Now, if you remember in our earlier uh, discussion, that I had told you that if you apply a certain amount of shear stress, only then the flow, that is there will be any deformation in your ink. So that we called as to be the yield value, as tau, we denoted it as tau 0. So what did we mean by that? We meant that let us understand the physical significance of this event. Let us say you are starting early in the morning on your press, and you have applied, or you have put some ink. Let us say you have put around 2 kgs of ink in the ink duct of your machine, offset machine, and simply you have you know ensured that the entire duct is filled with ink, and you have started operating on the machine, and the machine is running without any interference in the, or without any agitation of the ink in the ink trough by you. Now after a certain time, it may be the case where you notice that the ink or the solid areas, especially in your print, they are appearing more and more light in nature. That means the amount of ink that should be present in that area, that much of ink is not there. Okay. So you went to the machine, and you saw the ink duct or ink fountain, and you found out that the amount of ink is there, quite large amount of ink is already present in your fountain, but ultimately what happens is your ink is not moving forward and not coming in contact with the fountain roller, as a result of which the fountain roller is incapable of uh, taking up any ink from the fountain and transferring it onto the metering rollers, and the metering rollers also are not getting sufficient amount of ink, and they are not able to transfer sufficient amount of ink onto the plate and ultimately onto your paper. So that is the problem that you notice. Now the question here is, why does this happen? This happens because our offsettings mostly are something known as having this behavior. Actually, this is written, this hyphen is not given, but just to make you understand, I wrote this. Inks, especially offsetting, sheet fed offsettings, they exhibit this type of behavior. This is known as viscoelastic behavior. So what does this mean? This means that they exhibit, so let us identify both, or let us understand both these terms distinctively uh, on their own. So let us first understand what is the meaning of the term viscous, right? And then we will try to understand the term which is elastic. Now let us start with the term elastic itself. What is elastic behavior? That means you apply some force of deformation, it will get temporarily deformed, the object will get temporarily deformed. As soon as you remove that force, it will again go back to that original state, right? That means no permanent deformation is occurring in that object. So this is what elastic behavior is. What is viscous behavior? Viscous behavior is when you apply that amount of a certain amount of force, then there will be a permanent deformation in that object, right? That means there are weak forces of attraction in between the superstructures within the fluid, and once you apply sufficiently large amount of energy or sufficiently large amount of force into that fluid, then those forces between the superstructures will break down, and the a flow will start within that fluid, and the better to say, the fluid will start to flow. This is known as the viscous behavior of any fluid. And as I told you that what elastic behavior is, that is also now known. I am saying to you that offsettings exhibit both these behaviors. That is, it behaves like a viscous fluid as well as it behaves like an elastic fluid. So what does this mean? So how to test that? How to analyze that, and what significance it has to ink press interactions, and what problems can happen if this behavior is not known to the printer. Okay, so let us take a look. So for this analysis, what we normally do is we either take a cone and plate type of a rheometer or two plate rheometer. So the picture that I have given you is from a two plate rheometer. So what is this? This lower plate, or the bottom plate which is placed on the bottom, this is stationary. Okay, this is stationary. That means it is not moving, right? But the plate on the top, this plate is capable of moving. This plate is capable of moving either in these directions. So that means, and within these two plates you have placed your fluid, right? That means this surface of the fluid is stationary. However, this surface and the almost which is in contact with the upper plate, whenever the upper plate is moving, this fluid will also undergo some deformation. So this is kind of, you can say that the upper plate is applying some shear stress on this fluid, is it not? Now you see what we have done is we will apply some shear stress in such a way that the upper plate is moving either in this direction or in this direction, thereby making a complete total rotational amount of movement of 360 degree. So this is 90 degree and this is 270 degree, and ultimately when it again comes back, it in the original position, that becomes 360 degree. So what we have done is, this is the amount of shear force, and this is the deformation that the material or the fluid that is in contact with the upper plate undergoes. This is known as the oscillatory test. This is known as the oscillatory test. Why? Because the upper plate is kind of oscillating to and fro and making a complete movement of 360 degree in angular terms. So let us first try to understand what is happening. Now you see that this image, I will show you what actually happens, but this is an ideal case. So let me begin by saying that this is an ideal case, right? There are two curves, as you can see, both are sinusoidal in nature, right? What does it mean? What does this curve entail? It entails how much of deformation or how much of shear stress is applied with respect to the fluid that has been provided in both these curves basically. So as you can see, this curve is coming, or this curve is generated from the movement of the upper plate. This let us mark this as curve number 2, and this to be curve number 1. Curve number 2 is generated due to the movement of the upper plate. So what does it mean? What we have done, we have measured essentially the deformation of this upper plate with respect to time. That is what this curve number 2 is suggesting, right? So that means from 0 to 180 degree it is moving in one direction, and as soon as it has reached that direction, it is changing and it is going back to the other direction. So that when we have measured how much amount of deformation it undergoes, that is the amplitude. That is why this is sometimes also referred to as the amplitude sweep of the fluidic deformation. So what is the maximum deformation it undergoes? This is the maximum deformation it undergoes in either direction, right? The only reason that the curve has changed the direction is because the upper plate is moving in in both the directions, that is, it is moving both in back and forth. That is what it is doing, right? However, curve 1, how is the curve 1 generated? This is generated from the stationary plate. What does it mean? It means that the force acted upon on the stationary plate is how much that has been plotted against time or with respect to time. This force is required to keep or counter the deformation that the upper plate undergoes. We call curve number 1, curve number 2 as the preset curve, right? And ultimately the force that is acted upon on the lower plate to counter the force that is acting on the movable plate, that is known as the resultant. That means your gamma t becomes your preset, that is how much amount of force you are actually applying with respect to time on the movable plate, and in order to counter that force, how much force is acted upon on the lower plate, which is in contact with the, which is stationary and in contact with the fluid, that is known as the resultant force. Now let us consider certain scenarios what will happen. Okay, the image that I have shown over here, this image is, as I told you already, this is for a ideal behavior. Why did I say ideal behavior? You see, the amplitude sweep for both the curves, right? Or you can say the forces acting, shear forces acting on both the movable plate as well as on the, that is the preset and the result, both are uh, of same phase, right? This behavior is known as elastic behavior. This behavior is known as elastic behavior. Why this is known as elastic behavior? As soon, listen to this carefully, that as soon as we are applying any deformative force with the help of the movable plate, the fluid is changing its, or getting deformed, and changing its shape to this particular, whatever is the shape of the upper plate. But as soon as we are removing this deformative force from this, the fluid again is going back to its original state. So there is no permanent deformation within the fluid, and as a result of which there is no phase shift. But what about real fluids that we are talking about? What about, for example, as I show you here, what about the resultant when we do this type of experiment on offset inks? What is the result? So this curve will give you an overall result. You see, again, this one is your preset, gamma t is the preset, right? And tau t is the resultant amplitude, or resultant deformative forces that is acting on the plate, right? Here you see that you are applying a certain shearing deformative force on the fluid with respect to time. This is the original curve, right? But what if your fluid, initially in our ideal case, what did we see? As soon as we are applying some deformative force or shear force through this plate onto the fluid is changing its shape, and as soon as we are removing that force, the fluid again is going back to its original state. But in this scenario, what is happening? Consider a tomato sauce, consider our offset ink. What will happen? As soon as we are applying some force, as soon as we are applying some deformative force onto the fluid with the help of this upper plate and trying to move this upper plate, what is happening? The fluid is offering some resistance to the flow of this, or to this shearing force. Why it is offering this resistance? Because it is viscous in nature, it has got viscosity. That is why it is offering this resistance, and that is natural. So that means what? The resultant deformation that will occur in the fluid will differ from the actual amount of deformative force applied on the fluid in the first place. That is why if you plot the shear strain with respect to time in the fluid, which is a viscous fluid, in that case you will notice that there is a phase difference between the preset, that is how much amount of deformative shear you are applying, and the actual shear strain that is applied onto the fluid, because the fluid in itself is viscous in nature and offering some resistance to any deformative shear forces that is applied on the fluid. This causes a phase difference between the between gamma t and tau t, that is actual amount of deformative force applied and what is the resulting shear strain that is taking place within the fluid. In physical terms, what is the manifestation of this example in physical terms? Same thing. When you saw that example earlier, the example that I gave you, when you saw in your this press in your machine that the ink has stopped moving forward, it is kind of become a blob like thing and it is not moving ahead and not coming in contact with the your fountain roller. So that means what? That means initial deformation that you applied to it, that was not sufficient enough to cause a viscous flow within that fluid or that ink. So now what you have to do, you have to apply additional amount of force just to ensure that the ink starts to flow. This difference, that how much amount of force you are applying actually and after how much time it is starting its flow, this difference leads to this phase difference delta over here in this particular curve. Now let us try to analyze another factor which we call as the storage modulus and loss modulus, or you can say the complex shear modulus G star. So what is this G star? G star can be defined as the ratio between your shear stress amplitude, that is tau, and your strain amplitude, your gamma. So that ratio, how to find out that ratio and what is the the manifestation of that ratio in real world, let us consider that. So as I told you, let us talk a little bit about the complex shear modulus. Which is G star. So G star can be defined as the ratio between your tau and your gamma. So what is your tau? Your tau is the shear stress that you have applied, and gamma is what? The resulting strain. That means this is your this is the tau, which was your what type of deformation it underwent, and gamma, what was your original strain amplitude that you obtained, that was the preset value what you got. So the ratio between the two is the G modulus, shear modulus or the G star. Now how to find out the value of G star, that we have to analyze. So considering G to be a vector, G star to be a vector, it will have two components, one along the x direction, so one along the x direction, one along the y direction, right? Where you will notice that the resulting the resultant vector between the two directions, that is the x and y, will give you the value of the G star. And what is the value of x and what is the value of y here? What values or what other vectors will be present along the x axis and y axis? Then if you want to see that, along the x axis we will have what we call as the G prime, and along the y axis we will have G double prime. What is the meaning of G prime? G prime is known as the storage modulus. And G double prime is known as the loss modulus. I will explain what all these terms mean, but ultimately we will see that if this is delta, that means the phase difference that we saw in the earlier case, G star can be found out through some combination of G dash or G prime and G double prime, right? I will show you how that calculation is basically done. It's very simple. Hopefully from this example only you will be able to understand. If you take a look at this particular image, what is the value? If I want to calculate what the value of G star, how will you calculate that? What will be the value of G star? It will be tan delta. So tan delta is how much? G double prime by G prime. Now let us try to understand what is the meaning of these two terms, that is G prime and G double prime, right? Or what is storage modulus and what is loss modulus. See, when we are applying, what is the source of this phase difference? What is the source of this delta? We are applying some force onto the fluid, and until and unless we have crossed a threshold value, we have crossed our shear stress has crossed a threshold value, there will be no permanent deformation within the fluid itself. That means till a certain value of shear stress, no matter how much you increase the shear stress, until and unless you reach a threshold value of the shear stress, any deformation in the fluid will not be permanent. It will be elastic. The fluid will remain elastic in that threshold range. So what is the threshold value? We have already established in our earlier class that this threshold value, we call it as yield value. That means your shear stress, until and unless you are applying a shear stress which is greater than the yield value for that fluid, your fluid will remain elastic in behavior or exhibit elastic behavior and will not undergo any permanent deformity. So within this range, you are applying, let us say you are applying this amount of deformation, right? Or you are applying this amount of shear stress. So initially it is offering some resistance, and thereby the applied shear strain will not be equal to the preset value or preset shear stress. This will cause a phase shift between both these amplitudes, which we call as delta. So the concept of, from this only we arrive to the concept of storage modulus and loss modulus. You see, in case of your G prime, that is your storage modulus, which is measured in Pascal, this represents, from the name itself, if you look at the name itself, that is better to say that, let me also go ahead and write something within this. This is the elastic region and this is the viscous region of the fluid or in the curve. So your G prime or the storage modulus, this represents your elastic region of the fluid. In this region, you can say that your fluid will behave almost like a solid. That means any amount of deformative force you are applying to it, there will be temporary deformation, but upon withdrawing that force, it will come back, the fluid will come back to its original state. That means it is almost behaving like a solid, an elastic solid, right? But G double prime, that describes the viscous region of your fluid. As I already told you that our fluids are, especially offsettings, they are exhibiting viscoelastic nature. So this G prime or the storage modulus is describing or indicating that value, that modulus of stress or elastic modulus in this elastic region. But G double prime is describing the viscous nature of the fluid. As you already know that viscous behavior arises from the fact there is internal friction between the components, and whenever any body tries to pass through it or any shear force is applied to it, the fluid will try to resist this, right? But in case of your this elastic region, elastic portion of this energy, that is stored in the deformed material itself by extending and stretching the internal superstructures without exceeding the threshold value. Until and unless you are exceeding the amount of stress you are applying to the fluid, until and unless it is exceeding the threshold value, there will be no permanent deformation. Okay. So for viscoelastic solids, if this condition is given, that is when G prime becomes greater than G double prime, they indicate that they have a higher storage modulus than loss modulus. So for these type of fluids, the amount of yield value or the actual yield value for this fluid will be very high. So in these type of situations, you will notice that you require a greater amount of agitative force or greater amount of deformative force to be applied to the ink in order to simply start the flow. Now for your ideal situation, so for an ideal, as I started my lecture with the ideal elastic behavior, what will be the value of delta? Delta will be 0 degrees. If delta is 0, that means there is no viscous portion, no G double prime. So G, in this case, G double prime becomes 0. And why does it become 0? Because if tan delta or delta becomes 0, then and G double prime becomes 0, then naturally this entire thing becomes 0. So if there is no viscous nature within the fluid and your entire fluid is ideally elastic in nature, then naturally G double prime becomes 0. Now for ideal viscous behavior, what will be the value of delta? Delta will become 90, right? That means G dash in this situation will become 0. No elastic region in this case, right? And the value of tan delta will approach infinity, because you are trying to divide it by 0. Now you see, this loss factor, we call this tan delta as the loss factor. This is again plotted in certain cases, right? Now I will show you that what is the overall significance of the values of G prime and G double prime in certain fluids. What will this entail? These conditions that I told you, these are for ideal elastic and ideal viscous fluids. But in reality, what happens? Let me show you that. See, this is something that I was talking about, where that loss factor has been plotted. So G prime in logarithmic scale, this has been plotted. So G prime is your what? That is your storage modulus, and G double prime is your loss modulus. That is what we saw from here. G prime is your storage modulus and G double prime is your loss modulus. So two fluids have been chosen over here, and they have both been analyzed under a rheometer and applied various stresses, and their amplitude sweeps have been done, and through oscillator test amplitude sweeps have been created, and this type of a diagram has been formed with the data that has been generated. So what does it mean? What does this indicate? In case of fluid 1, you will see the value of G prime is greater than the value of G double prime, whereas in case of your fluid 2, the value of G double prime is greater than the value of G prime. What does this mean in real life? G prime is what? G prime is your storage modulus. If your storage modulus is higher than your loss modulus, that means it is more elastic in nature than it is your viscous. And conversely, if your G double prime is greater than G prime, then naturally the loss modulus is higher. That means what? The fluid is more behaving like a viscous fluid than an elastic fluid. So what does it mean? This means that for fluid number 1, this example, the amount of yield value or the amount of stress, deformative stress, that is needed to be applied to the fluid just to start the flow of the fluid, to ensure a good flow of the fluid, that is very high. That is very high. Because why? The storage modulus is greater. It will, when storage modulus of any fluid is greater, it will resist any type of permanent deformation, and as soon as the deformative forces are withdrawn, it will try to get back to its original form. But in case of fluid number 2, what is the ultimate result? That your loss modulus is greater than your storage modulus. That means what? That it is normally behaving like a viscous fluid. That means the tendency of this fluid to start the flow is already quite high. Here, the amount of yield value required to start the flow will be quite low in comparison to fluid number 1, right? So this is the first inference that can be drawn from these two plots. There is another inference that has to be drawn from this plot. See, the values for both this G prime and G double prime in both the curves or both the plots are decreasing, right? They are decreasing in nature, but they are decreasing only after a certain point. This is the point. Till this point, both the storage and the loss modulus, both of them, they are not changing. That means they are remaining constant in this region, right? They are remaining constant in this region. This region where storage modulus and loss modulus for a certain fluid remains constant, that is known as the linear viscoelastic region, or LVE, linear viscoelastic region. What happens in this region? This you can say that this point, basically this is the point where you have your amount of deformative forces have overcome the yield value for this fluid. This is the point where you have reached, or you have overcome tau 0 to achieve this value, to achieve the flow of the fluid, right? You will notice another thing, that the range of this viscoelastic region for fluid number 1 is quite larger than that of in comparison to fluid number 2. This indicates also that the yield value, that first inference that we drew, that the yield value in this particular fluid is quite high, that matches with our analysis. In this region, within the linear viscoelastic region, there will be no permanent deformation or any amount of force that you are applying to it that will not cause any permanent deformation to the fluid. That means this entire region is elastic. Within this entire region, your fluid will become or remain elastic in nature, both the cases, right? But as soon as the amount of shear stress you are applying is crossing that yield value, this is the region where your viscous flow starts for the fluid. This is the region where the viscous flow. See, in case of viscous flow, both G prime as well as G double prime are decreasing. That means what? The viscous flow of the ink, the fluid in both 1 and 2, that has started. And within the elastic region, no matter how much amount of force you are giving, since it is not exceeding the yield value, no permanent deformation will occur in the fluid, and the fluid will remain elastic in nature. Okay? So this is exactly the problem that I was talking about earlier, that what is the overall effect of this high yield value. See, this is the fountain roller and this is the ink duct of a machine, an offset machine, let us say, right? You applied ink onto this, you have poured ink in the duct, and you are considering the ink profile for 3 inks, ink A, B and C. You see, for ink A, it is maintaining a very steady flow. That means a steady profile has been maintained and almost the entire ink is in contact with the fountain roller. That means it is moving ahead. It is flowing towards the fountain roller. That means it is exhibiting viscous behavior. In case of B, it is the amount of ink that has already moved ahead towards the fountain roller is quite high. That means the amount of viscous flow in the ink B is quite high, right? But in case of ink C, you will see that after moving to a certain distance, the flow has stopped and it is no longer, this ink C is no longer in contact with the fountain roller. That means the fountain roller and the machine is not getting any fresh ink from the ink duct. So what inference can you draw from this particular 3 inks? See, it has been written also that ink A, this has got a low yield value and low viscosity. Because it has got low yield value and low viscosity, it is maintaining a good profile, and it is almost the entire ink is maintaining a steady flow. But in case of B, it has got a high yield value and high viscosity, right? Why it is moving in such a way? Because you see, because it is highly viscous in nature, along with high yield value, almost the entire ink not only has moved ahead and come in contact with the fountain roller, but you will see, it has become like a blob-like structure. Due to which factor? Because of the factor that it has got high viscosity. But for A, since it has got low viscosity, the cohesive forces acting between the molecules, these are relatively lower and they are remaining far apart. But in case of ink B, because the cohesive forces are very strong within the fluid itself, it is accumulating together in a certain area. As for C, it has got high yield value and low viscosity. That means because it is low viscosity, it is staying far apart. But again, since its yield value is very high, that is why it is unable to move on its own free will until and unless acted upon to do so. This problem, when this happens, that ink is staying back onto the ink duct and not moving ahead and coming in contact with the fountain roller, this problem is known as hanging back problem, as written also. This problem is known as hanging back problem. This will cause problems in ink distribution as well. If your ink is not coming from, from the duct, uh, ink duct to the fountain roller will not have any more amount of ink to pass on to the metering rollers, and thereby the printing process will be hampered. Okay, and if the fountain rollers, or your not fountain rollers, sorry, the metering rollers does not have enough amount of ink, right, to transfer from one roller to the other, it is a convention, we say that if the thickness of ink film in the preceding roller is 2, then half of that ink is transferred to the succeeding roller. So if the preceding ink does not have sufficient amount of ink to transfer to the next roller, succeeding roller, then we face a problem. That means the string formation will occur. That means instead of this half amount of ink or a smooth film of ink transferring to the succeeding roller, there will be a breakage in this film, and this string, the ink will get transferred in the form of strings, right? If you have seen, if you have made some caramel, that is, you have mixed this sugar inside of water and heated it, and you have taken it between your fingers, you will see that some strings are forming when you are separating your fingers with the caramel between your fingers. Those type of, that means what? It is not transferring from one finger to the other. Not sufficient amount of this material is present in one finger to get transferred smoothly to the other finger. So that happens. This problem causes mottle. Mottle is what? So let us say you are printing a very solid area in your during your printing. So what do you expect? That the density, optical density of this solid area will remain uniform, or will remain high throughout this entire solid area. But because your ink metering rollers and your foam rollers and your plate blanket is not receiving enough amount of ink, that is why the density of this area, the solid area, will vary, and it will appear as if that in some areas the density is high, some areas density low, because uniform distribution of rollers, a uniform distribution of ink between the metering rollers, that has not happened. This mottle can also form due to another factor which we will discuss later on, which is the tack value. If the tack is very high, then you will not be able to transfer it from one roller to the other. That will also be another problem. Now again, in this, another important factor which will determine your ink's performance in the press, that is the emulsification. I think I had another picture. If I get it, I will show it to you. Emulsification is an important factor. Why? Because in your image area you need to form water in ink emulsion, but in your non-image area you need to form just the opposite, that is the ink in water emulsion. That means in your image area the amount of ink will be higher, water lower, and in non-image area amount of water higher, ink lower. Now it depends upon the water uptake capacity of your ink to determine how well your emulsion will be. Why is it important? Because if the amount of water that is uptaken by your ink is quite high, then this balance in the image area between water and ink, that will suffer, and automatically what will happen, your densities will come down. In your non-image area, if this balance is disturbed, that is, amount of water is lower than amount of ink, right, then that means the ink is taking up much of the water. So if this balance is disturbed in non-image area, what is happening? In the non-image area, ink will start to grab. That means scumming will occur. Image will come in the non-image areas as well, right? So that is why understanding emulsion and emulsification capacity of the ink is quite important. We normally do this test. What we do is there are certain machines, automated machines, and we get this type of curves. I'll explain it to you. We take a specific mass of ink, let us say 25 grams of ink in a cup, and then there is the cup, a spindle is actually inserted. So let me just show you. This is the cup. There is a spindle which is having some uh, this fans, and that spindle is, this is the amount of ink. Spindle is dipped inside of that cup, and the spindle is rotated at certain speeds. Okay, these certain speeds are fixed by dependent on what printing process you are using, and then we add some specified volume of water or fountain solution specifically per minute. Okay, so that means we are testing what? We are testing how much of the water can be accepted or taken up by the ink. And what is the spindle doing? The spindle is rotating. That means it is generating some torque. Now, initially when the spindle is rotating, the amount of torque will be quite high. Amount of turning force required by the spindle to move or rotate will be quite high, because the ink is having very high viscosity. But as soon as we are adding water to it, and after a certain amount of time, what is going to happen? The torque is going to come down or drop. That means the viscous nature of the ink will be lowered. The viscosity will come down because water has been added to it. So the amount of turning force required by the spindle will also go down. Now there will be a time, there will be a point in time when you will notice that the amount of water has exceeded the emulsification capacity, EC percentage, for that ink. And at that point, there will be a complete phase separation between the ink and the water, or within the water, within the ink itself. Initially, what was happening? Initially, the emulsion was forming between ink and water, where the amount of ink was higher and water was lower. But there will be a time when the reverse will happen, and there will be a phase separation. So at that point, a distinct will be able to, even if you don't look at the chart, uh, this chart can be obtained in real time actually. Okay. See, this is A and B are for different inks, torque values for different inks, and the amount of water that has been added has been steady, and after a certain time, amount of water has increased really. So at that point in time, there will be a sharp drop in the torque, This indicates what? The ink is not able to provide any viscous resistance to the movement of the spindle. Thereby, the amount of turning force required by the spindle to rotate has dropped down sharply. At this point, you will notice that this is the maximum emulsification capacity percentage for the ink. That is, this is the maximum amount of water that can be accepted by the ink without phase separation. So you will note this down to be the EC percentage. Okay, so this is how we do emulsification tests. Yes, and as long as we are, this is another important curve. So as long as when we are increasing the speed of the machine, naturally the amount of water or fountain solution that is required for ensuring good image non-image separation on the plate, that will increase. Okay, so that is what it is shown. So here, as you see, the impression per hour is increasing. So as the speed of the machine is increasing, the amount of fount required is also increasing in percentage terms. That means quick separation between the image non-image areas is required in this case. Okay. Yes, this is a picture that I took myself in one of the during our when I visited a press in Northeast. So there this problem occurred. You see, this is what happens. The problem was caused because of some other factor, but I'll just show you one example. Let's see which component is this, which component or which part of the machine is this. Just try to answer it for yourself. Pause the video here for a minute and answer it for yourself. This is the fountain rollers, basically fountain section. So this is the tray in which the fountain comes from the dampening tank. The metal rollers take the water which is in contact with rubber rollers, consecutive metal and rubber rollers ultimately take it to the form rollers in the plate. Plate is somewhere over here. Okay, plate is somewhere over here. This is the ink form roller. These are the dampening form rollers, and it is applying the ink and water onto the plate. So this part is basically the fountain section, or dampening section of the machine. So is the ink supposed to come into the dampening section of the machine? No, ink is supposed to come only into the plate through the inking system, ink metering system, ink train. But in this case, there is a problem. You see, the ink has been taken up by the fountain rollers of the machine as well. If that means what, that the non-image areas of the plate will also not only receive water, but it will also receive this ink. That will cause what? That will cause scumming. The reason for this particular problem that I visited was different, but these problems will occur when the balance, ultimately the cause was that ink water balance was not right. Okay, so that means in your plate the image area will have a fine balance of water and ink, and in your non-image area it will be ink in water emulsion. If this is disturbed in certain ways, if the tendency of the ink is to take up more and more water, then this type of problems will occur. There can be other reasons as well, mechanical reasons as well, but I am only talking about from the perspective of the ink itself. Okay, this can be one of the many reasons that this can happen. Not the only reason that this can happen, but one of the many reasons that this can happen. There are other mechanical factors also. Roller pressures are involved. Other machine operating conditions are involved. Dampening water's pH conductivity is involved. So many other factors are there. But of those many factors, this is also one factor, since we are talking about ink and fountains. Okay. This is another picture that I took in one of the press here in Kolkata itself. This is what we normally refer to as. So now in this part of the lecture, we are only going to discuss about the certain problems that we are facing due to ink. This type of problem is known as misting, not flying, because nowadays flying does not really occur. Misting occurs. What happens is, so how did I get this, or what does this picture actually mean? So this is normal A4 sheet paper. One of our customers, we received a complaint from them that they are seeing that there is some flying and misting problem with your ink, one of your inks. Misting means that during when the press is running, mist of ink will get sprayed out from the inking rollers and spread all around the machine and all around the room. So let us say if our magenta ink is facing this misting problem. So let us say you have started printing from 9 a.m. in the morning. By 12 noon or by evening, when you finish printing, you will find out that not only the entire machine section of the magenta unit, but other sections of the machine are also getting sprayed by or having this mist of magenta ink. That means the kind of mist of magenta ink is coming out or getting sprayed away from the inking rollers of the magenta unit. So why does this happen? First of all, why does this happen? That you have to analyze. This happens for many reasons. First, the temperature is not, of the roller systems or roller train is not controlled. That is one reason. Okay. For very high temperatures, the viscosity of the ink has gone so down that it is getting sprayed out, mist is forming. Second, pigment wetting has not been done properly within your ink, or there has been problems of the pigment particle, the specific gravity of the pigment that you have chosen, that is quite low, that it is not present within the, or not trying to get dispersed, remain dispersed through within that vehicle of the ink. So because of all these problems or all these reasons, this type of misting problem can occur. So what I did was, I simply took a piece of A4 sheet of paper and I, if I show you the earlier picture, see, this is basically the inking section. This is basically the inking section. This, in modern machines, they have these grills. Earlier machines, they were completely open, but nowadays they have grills. So what I did was, I applied this paper in one of the grills such that this part of the paper, at least you'll see here, you'll see the grill marks, but this part of the paper was loose, so that any mist that was coming out of the rollers would form and sit on the paper. I applied this sheet of paper on all the units, that is cyan, magenta, yellow, black, and then took out the paper at the end of the day. I went to the press in the early morning entire day they printed, and in the afternoon, on the evening time, I took out the paper and I saw what was the result. I made a comparative analysis, visual analysis. This is one very good way to analyze the misting problem. So then I suggested certain temperature control measures and also the dampening control measures, and then the problem was fixed. So this is what the misting problem is. How does misting differ from flying? Flying, in case of flying, you will see that here the droplets of the ink is it can be viewed as fine droplets. But in case of in case of, this is the misting problem, but in case of flying problem, the droplets that will emerge out of the inking rollers, that will be quite large. Okay, large drops of ink will come out, but that does not happen. Modern ink making has become so sophisticated that flying problem does not occur, and even this misting problem is a very rare problem. Okay, so this does not occur generally. Only if the temperature is not controlled uh, quite nicely in the press, and you are printing full solid jobs, that means the ink uptake or the ink percentage in your rollers is quite high, right? Ink release is quite high. Only these during these problems, these situations, this type of problem can occur, but this is also very rare. Next, this is okay. I will not show you the curve first because this curve is already known to you. Let me show the, wait, I think I have that. Yes, Tack I have. Yes. So this is what is known as the inkometer. Okay, as I referred to earlier also, this is a digital inkometer. This instrument is used for measuring the tack of the ink. What does tack mean? Tack is that stickiness of the ink, right? As I already told you, this is what? This is mottle formation. This is mottle formation. See, ink film is, instead of a smooth separation, these are two metering rollers, right? So between the two metering rollers, the ink, when they are coming in contact, a smooth separation is required. But when they still string formations are occurring, these filaments are occurring, then this will cause this mottle problem. That means the tack of the ink is quite high. It is not trying to release. The stickiness of the ink is causing a disturbance in smooth separation of the ink films between two rollers. It is not possible for us to ensure a smooth separation between the films because the tack is quite high. It is not letting go of the ink film, is not letting go of the other roller. This is one problem, mottle formation due to high tack. Another problem due to high tack can occur in the your blanket and your paper. If the ink tack is quite high, and when it comes, ink blanket comes in contact with the paper, after it has been printed, the ink film having high tack will not let the paper go away very easily. It will try to pull the paper, causing some fibers to come out. These type of printing defects. See, so this type of printing defects. So from here, from this region, all these regions, the ink tack being very high, the ink pulled away the fibers of the paper from these regions, causing this type of problems. Okay, so these are the problems that can be caused due to high tack. So how is tack measured in our lab? Tack is, I will explain this tack stability once again, but let us first understand how tack is measured. So here you say there are three rollers essentially, okay, and we apply a certain volume of ink with the help of a pipette on one of the rollers, and then at a certain RPM we switch on the machine. That means the rotational velocity of this rollers is fixed at certain RPM depending upon what printing system or the printing process you are trying to simulate. What will happen? Because the value of tack when there is no ink here will be considered as 0, right? This is your base threshold. After applying the ink onto this and you switch on and it is rotating at certain speed, that value, this value will be calculated. So what is the 0 value? This 0 means the amount of, this 0 is just an example, but this is what I wanted to say, is it's a base value. The amount of torque that this rollers is required, or it is essential for the rollers to apply, the amount of torque, the value of the torque that this rollers needs to apply to split the ink film and continue its rotation, that torque value is calculated. Okay, So naturally, the amount of torque required to rotate these rollers when there is no ink, that is considered to be the base value. So after applying the ink, the amount of torque will increase, the value of torque will increase. Why? That ink is offering some resistance to the rotation of the rollers. So naturally the amount of torque will increase. So this torque, additional torque, from this additional torque, we can get that value of tack. So tack is essentially measured in gram meter. So sorry, not gram meter, actually it is Newton meter. Sorry, it is measured in Newton meter. Newton meter is what? Force into distance, unit of torque. So ultimately the measurement of tack is nothing but the measurement of torque. So greater the torque, greater is the tack. But we want, so now coming back to this tack stability curve. So this is again known as the tack stability curve. Here it is written as press stability, but we normally refer to as tack stability. I've already shown you this curve when we were talking about distillates. One was aromatic free and the other was regular distillate, if you remember that. So here you see what we have measured is, we have started this machine, we have applied this ink, and we have started this machine, and we are measuring this display will give you the tag values at certain intervals. We normally take the values at 1 minute, 2 minute, 3 minute, like this, and then the corresponding values of tag that we get from the machine, that is plotted along the y axis, and the time is plotted along the x axis. So two inks we have chosen, and the tack stabilities of, and ultimately all those points are joined to create this curve, which are known as tack stability curve. So the tack stability curve for two inks are given, A and B. So whose tack stability is better, do you think? Of course for B. Why? You see, for A, very rapid increase in tack and very rapid decrease in tack. Okay, but for B, there is a steady increase in tack. And why does tack increase first? Because first the solvent part, that starts to evaporate at higher rotational forces because heat is generated due to friction, and after a certain time, why does it start to fall down back? Because the viscous movement or the viscous resistance offered by the ink, that reduces, because it is constantly moving. That intermolecular forces of attraction, cohesive forces of attraction between the superstructures of the ink, that goes down, so the tack decreases. But that is one thing. But the point that I'm trying to make here is that between A and B, which ink will perform better in press? Of course B. Why? Because the tack stability is quite, the tack is quite stable in case of B for this ink. What is going to happen if we are using A in the press? Very quickly the tack will increase. So that means that will cause all those problems. Mottle formation, it will happen. Ink will not be transferred uniformly. Then this type of your paper will be torn away. Wave break will happen if you are using wave. All these things will happen. And after A, when tack drops rapidly, what will happen? Again, ink transfer will not. Tack is responsible for ink transfer. That stickiness is required for ink transfer, but too much stickiness, too much tack will not ensure good transfer, and too low stickiness, when the tack is very low, that also will not ensure good ink transfer. So an optimum level is required. That is why this type of curves, we avoid inks having this type of curves, tack stability curves. This is a good curve, B is a good curve. Okay, so tack is clear. Then we have viscometer. I am not going to do in this lecture. Okay, then we have this flocculation, as you know already, that when the dispersion of the ink has not been done properly, or you can say that the amount of surfactant or the type of surfactant that has been, or wetting agents and the alkyd resins that has been used in the ink, that is not doing its work properly, or you have chosen wrong wetting agents, then what will happen? The pigment particles will try to coagulate. When this problem is aggravated, when it comes in contact with the fountain rollers. That means in the plate, or on the plate, there the ink comes in contact with the fountain roller. At that point, what will happen? Because this water will start to fill out the gaps within the pigment particles, or within the ink emulsion, and there the vehicle component will slowly, because the amount of attraction between the vehicle and the pigment is not that high, the vehicle component will start to get separated and the pigment will start to flocculate together, and then they will pass into the water. And when sufficient amount of pigment particles are flocculated into the dampening solution, and again the amount of dampening solution will again transfer from the fountain rollers of the machine to the dampening tank, this will change the color of the dampening tank. See here, yellow ink has flocculated. Okay, yellow ink has flocculated, changing the color of the dampening tank to be yellow in nature. All right.